All right. Now, since the colligative properties depend only on the number, not the type of particles in solution, electrolyte solutions are going to be different than non-electrolytes. Okay. Now, electrolyte, remember, is something that conducts electricity in aqueous solution. So, essentially, it's an ionic compound. So, if you have a non-ionic compound, you dissolve it in water. Okay. It dissolves in water. Excuse me, because of hydrogen bonds. Whereas an ionic compound over here separates into ions. So for sugar, 1 mole of this gives you 1 mole in solution. But for the ionic, 1 mole of sodium chloride gives you 2 moles of ions. So we would expect twice the effect on colligative properties. We account for this with I, which is called the Van't Hoff factor, named after someone, and I is the moles of particles in solution divided by the moles of solute dissolved. So for this, it would be 2 over 1, which would be 2. For this one, it'd be 1 over 1, so it would just be 1. And it's going to be 1 for all of our non-ionic things, which is why we didn't have it in our first equation. But when you look at these equations, you'll notice they're exactly the same as what we had before. We just have to add the I to it. The expected I is the number of ions it produces, but the observed I is going to be a little bit less because we don't have complete dissociation. And the higher the solution concentration, a greater difference there is between the expected I and the observed I. There's a chart on page 536 that shows you the comparison between expected I and observed I. So let's look at this. Which solution would have the largest freezing point depression? Well, freezing point depression is so what I didn't say in this question that would be important, but I did say in the question, left it out for the HF by mistake. These are all aqueous, so they're in water. Okay, F for water is 1.86 degrees Celsius times kilograms per mole. So, this one. This would separate into 4 ions. So we would have 4 times 1.86. And the units are going to be degrees Celsius times kilograms per mole times moles per kilogram, which comes to degrees Celsius for all of them. So we have 4 times 1.86 times 0.01. So we have 0.0744. Now this one is going to separate into 2 ions, and it has twice the molality of the first one. So we have 2 for our I, 1.86, and then we have 0.020. Notice the I is half, but the M is doubled, so it's going to come out to be the same thing. Our third one here, we're going to separate into 1 calcium and 2 bromines, so we're going to separate into 3 ions. Our fourth one here, H and F, we would separate into 2 ions. So 2 ions and 0.20 molar, that would be the same as number 2. So let's look at the third one. 3 is our I, 186, and then 0.020. And just looking at the setup, we can tell that one is going to be the highest, even without putting it in the calculator. .1116. Now I want to talk about this one more. Because it was with all of these others here, we assumed it separated into ions. However, HF is a weak acid. So we would consider it undissociated, which would mean that the I, the Van Hoff factor, would be 1. So it actually would be even lower. .0372.